presentation of the day, telling us about random spanning forests on graphs for fast Laplacian-based computations. So Nicolas is from Grenoble, from gipsa-lab.
Thanks, Remy, for the presentation. Thank you for inviting me as well. I have two apologies to make. The first one is that I'm only here one day, and I'm very sorry about this. A lot of constraints currently. And the second apology is for the people from Lyon, especially, who already heard this talk maybe like 2 months ago. It didn't change a lot since then. So I'm very happy to present this work here. Maybe the first thing I want to talk about is why am I here? It's a very broad subject, DPPs, and I've seen from the list of people who talked here, well, it comes from very different places, and I'm going to explain from where do I come from and what's the motivation behind it. And then I'm going to talk about other stuff. So the first, so the motivation I have, it comes from graphs. So I consider a connected graph with n, so small n here. Is there a laser in here? Yeah. Okay, laser. Sorry, I'm learning.
Yeah, the big middle button is the laser.
Okay, I didn't see it. Okay, thanks. So little n here will be the number of nodes throughout the talk, and little m will be the number of edges. So I'm going to talk about spanning trees, and I'm very happy that Adrien talked right before, because there are actually many connections between what he does and what I do that are quite interesting. So a spanning tree is a subset of edges that are connected, do not contain cycles, and span all nodes. Okay, so for this graph here, this is an instance in red of a spanning tree, and this is not a spanning tree. So it is spanning, yes, it is connected, yes, but it contains a cycle here. So this is a unicycle. This is what, but I don't care about unicycle in this talk for now. So those spanning trees, so there are many spanning trees in general in a graph. The worst case is one, just in a linear graph, there's only one spanning tree. And the case where there are the most spanning tree is the fully connected graph, where there are n to the power n different spanning trees. And so given this huge collection of spanning trees, well, a very popular object is a uniform spanning tree, which is just drawing one spanning tree uniformly out of all the possible ones. So this is called a uniform spanning tree. And the classical result, and this is the connection with this workshop here, is, well, a UST is a projective DPP defined over the set of edges. Okay, now to give you the flavor of this talk, so DPPs can be understood as weakly repulsive summaries of a ground set. So here I'm going to talk only of discrete DPPs, so basically edges on graphs. So it can be understood as a weakly repulsive summaries of a ground set. And a general, maybe machine learning or signal processing question is, well, given a summary, what information am I able to extract from the ground set? Okay, so this is my point of view here. And when I translate this on graphs, one way of translating this question is, well, given that USTs and their generalization that I'm going to talk about, random spanning forests, are DPPs, the question translates as, okay, so I have a graph here in the middle, and what can I learn from this graph given a collection of USTs? Okay, so I draw a few USTs, and I'm interested in answering the question, what am I able to capture from the original graph? So there's a trivial example, a lower bound on the maximum degree. Say I want to estimate the maximum degree of this graph. Okay, well, if any UST, if I take the maximal degree of a UST, well, this is a lower bound on the maximal degree on the original graph. Okay, so this is not very interesting maybe as a question, but this is the type of question I'm going to try to ask. Okay. So throughout this talk, I'm first going to motivate why do I want to compute some of the things I'm going to estimate in this talk. Okay, so there are a few types of computations on graphs that can be accessible with USTs. I'm going to motivate those type of computations. And then I'm going to concentrate on one example, which is the inverse trace computation. There are others that we work on, and I'm going to talk about those last ones in the extensions in the last part here. Okay, so what am I trying to compute on what type of data? So graph-based data is very general, very versatile. Here are some examples. This is the internet, or an image of the internet network of computers connected with Ethernet links. This is an image of white matter in the brain. This is an image of a graph of transportation of electricity in Europe. Transportation network of humans here. And there are also other types of data, like point clouds, where the graph is not, let's say, native from the data, but you can construct the graph from the data by nearest neighbors, for instance, or something like this. Okay, so what I'm going to talk about, when I say graph-based data, in general, there will be a connectivity structure. So here, this is an instance of a graph. I have the adjacency matrix, the degree matrix, and the Laplacian matrix, which is one minus the other. And possibly a signal on the nodes. Okay, so on each node here, I might have some information. It could be the number of people going through the station in a transportation network. It could be the amount of blood flow in a voxel in the brain. It could be those type of information. It's defined on the nodes. It's defined on the edges. For simplicity here in this talk, I'm going to consider signals defined on the nodes and just scalar signals. Okay, so you could define, like Adrien did before, you could also say on each node there is a vector in R2 or in Cn and whatever. I mean, you can imagine different things, but just for simplicity here, it's just a scalar. So here, a list maybe of different operations one can do with these graph-based data. What can we try? What's interesting to do on this data, to compute on this data? So there could be, for instance, community detection. So on the graphs, community detection. So finding groups of nodes that are more connected with each other than with the rest of the graph. There are questions of graph visualization, for instance, also. This is the type of computation you might want to do on a graph. And on signals defined on graph, you could do denoising. Okay, say your graph is a sensor network. Okay, you're measuring temperature in France, and you have a sensor network, and two sensors are connected if they are close to each other in space. You might want to denoise the network. The signal that is measured on the network. This is a type of operation you can do on the signal that are defined on graphs. You can try to do signal compression, sampling, any kind of classical signal processing operation you might want to do on a classical signal. You can actually do it on a signal defined on a graph. You can do interpolation. Graph filtering is another example where you want to filter the signal, as in the classical signal processing Fourier filtering paradigm. You might want to do this on the graphs, and there are applications in graph neural networks currently that actually use those filters. Okay, there are many different examples, and some of these examples are based on the Laplacian matrix. I'm going to motivate 3 of them, or maybe 2. I forgot if I have still 3 in the slides or not. It will depend on the time. At what time did I start? 10:30?
Maybe a little later.
Okay.
35, say.
35, okay. So here's the motivation for signal denoising on graphs. So first, maybe signal denoising is not very familiar with everybody, so I'm just going to talk about the 1D classical denoising case. So I have a bunch of measures here in time, okay, and I want to estimate the underlying signal that I'm actually measuring, okay, the ground truth in a sense. So this is one option. So how did I do this? Well, by just doing a sliding window and just spotting the mean on a sliding window. Well, this is a bit frustrating because you don't really know what you're controlling here. Are you actually denoising? So there's a whole paradigm, let's say, in denoising where you actually assume there is an underlying data X that you're trying to infer from the data. You have noisy observations, so the little dots I had are yi of the signal measured in Ti plus the noise, and I suppose that this noise is, for instance, Gaussian. Okay. And we seek to estimate x from the noisy observations y. The following estimator is very classical. It's called a Tikhonov estimator, and what it is just an optimization problem where you try to minimize a sum of two terms. The first term in green is the data fidelity, okay? So how far am I from the measure? So Z in R is, well, Z in the space of the signals is what I'm trying to optimize over. YTI here is what I actually measured. Okay, so this is here is the sum of the error I do compared to what I actually measured, called the data fidelity. And here, you want to regularize this problem, okay? Because you don't want you suppose that your signal is noisy, and you don't want the derivatives to change a lot down the time. Okay, so and when you optimize this object here, you actually find different solutions given the trade-off here, parameterized by Q, which is just a scalar, a positive scalar. Here's a few illustrations. So I have my observations Y. For a given Q positive, I have some solution. And if I increase Q, so this is for large Q, I'm giving a lot of weight on the data fidelity. I'm obtaining something that is very close to my measures. Okay, and for small Q, I'm going to smooth. And in the limit Q goes to 0, I'm actually computing the mean of the signal. Okay, so this is called Tikhonov denoising. It's very classical in 1D. It's not so classical for a signal defined on a graph, but actually you can generalize this problem very easily on graphs. The first way to observe this is that the regularization term can be written in a very compact way as Z transpose LZ, where L is the Laplace operator, the discrete Laplace operator, which is equivalent to the Laplacian on the path graph. Okay, if I have this path graph here, I compute its Laplacian as I showed you before, and this is the discrete Laplace operator. So by generalization, you can say that the so-called Tikhonov regularization problem can be computed, can be written this way. Okay, here where the regularization term is just Z transpose LZ. And in this case, with this writing at least, you have an exact solution, which is x hat. This solution here is k times y, where k is this inverse regularized Laplace operator. Okay. Now, written this way, you can generalize it in a sentence to graphs, to any graph. Okay, now I have any graph, arbitrary, just connected, let's say, it's just simpler. I have a signal on this graph, and I have a noisy measure of this signal here, and I try to denoise. Well, you can you can use the exact same paradigm for signals defined on graphs, where L here is the Laplacian operator of the graph this time. Yeah, you can know that this smoothness penalty here, Z transpose LZ, is really, you can understand this smoothness operator because you can rewrite this equation here as the sum over all edges of Aij, which is the weight of edge ij, of the difference square between nodes, between the signal and the nodes connected to this edge. Okay, so the analytic solution is the same. It's just that the Laplace operator here in 1D is just a discrete double derivative operator, and for the signal defined on the graph, it's just the Laplacian matrix of the graph. So this is the first type of problem, type of computation we might want to do. Okay, so I have a Laplace, I have a graph, I have its Laplacian, I have a signal y, and I try to denoise it. I want to compute this. Okay, so I want to invert qi plus l. This takes, in general, in a naive way, let's say, it costs n cube, where n is the number of nodes, n cube operations to actually do this. In many cases, this is too much. And so the goal here of this talk and of kind of the work I'm doing since a few years is, well, how can I estimate this invert here? without inverting the Laplacian? Is there another way? And it turns out that yes, you can actually do this operation by using random spanning forests, and I'm going to talk about this later on. A second motivation is very similar. I'm not going to go into details here. It's called semi-supervised learning on graphs. So the problem you have is that you have a graph, okay, and you know that the node here is in community blue, and node here is in community red, and you try to infer the information of which nodes are in which community. Okay, you're trying to actually solve this problem here, go from here to here. This can be understood as well as some sort of denoising. Not going into the detail. At the end, the operation you're trying to do is very similar to the one you had before. It's just that, okay, this is the new k you have, where q here, it's not qi anymore, it's just some diagonal matrix q with positive entries on the diagonal. So it's a generalization, let's say. But the actual computation is very similar. Now, another motivation that is very related to this denoising problem is, well, there's a huge question in this problem is, how do I choose q, the small parameter q? This is a very common problem in optimization. And there are some ways of doing this. And one of them is to compute the degrees, the effective degrees of freedom of this linear smoother k, that was a qi plus l minus 1 qi. And by actually computing this trace here, you gain some information on how to choose the parameter q. I'm not going to go into the detail, but there are some choices of parameter that follow some criterion, like the IIC, like GCV. And okay, there are several techniques that use this trace. Okay, so you want to compute this trace to have some information on how to choose q. While computing this trace, again, you need to solve the inverse of the Laplacian. So how can I compute this trace here without inverting the Laplacian? A last motivation, I didn't know if I had left it, but I did leave it. So I'm going to talk about it. I think it's very interesting. Okay, effective resistances. First, the definition. LDAG here is the Moore-Penrose pseudo-inverse of L. And the effective resistance is just a definition. It comes from an interpretation of the network as an electrical network. The effective resistance of any edge is defined like this. So it's the ith entry of LDAG plus the jjth entry of LDAG minus 2 the entry of LDAG that is in I and j. A property is that, well, PE here can be understood as a probability. So AE is the weight of edge E, and RE is the effective resistance of edge E, and it can be understood as a probability distribution just because all the terms are positive and you just need to normalize. So what is that useful for? For instance, for spectral sparsification, and after this comes a beautiful theorem just after the definition that you need to have is, so I have a graph G and L is Laplacian and H is a subgraph of G. Okay, so it's a sampling, it's a subset of edges of G of same size, but hopefully much sparser. But when I say same size, I say the subgraph has n nodes as well. It's just much sparser, so the number of edges of the subgraph is much lower, and I call X its Laplacian. And I just say that definition H is an epsilon spectral sparsifier of G if it follows this inequality here, where the inferior equal here is understood as in the PSD, positive semi-definite sense. Why is this useful as a definition? For many things. If I have such a X, I have, for instance, that all eigenvalues of L are epsilon approximated by the eigenvalues of X. So this is one instance of one reason of why this is useful. And there's this beautiful theorem. It comes from a line of work from Spielmann of the 2010, 2009, even before in some parts. So the theorem goes like this. You have an epsilon and you sample m edges IID with replacement according to P, this probability here, that is proportional to the effective resistance. And if you do that, you obtain a subgraph, of course. And if you properly reweight those edges, I'm not going to go into this, then this subgraph is a spectral sparsifier with high probability if m, so the number of edges you've sampled, is larger than n log n, where n is the number of nodes. What does this tell us is that those effective resistance are very important because if I have access to them, and if I sample according to these effective resistance, I obtain a spectral sparsifier very fast in n log n edges. Now, of course, the hard part here is the effective resistance computation. And this is another motivation of my work is how do I obtain those effective resistance here without actually inverting the Laplacian? So the more pseudo-inverse. Before I had a true inverse because I had L plus Qi where Q is strictly positive. But L is not invertible. It has at least one eigenvalue equal to 0, so we use the more Penrose here. So this is another motivation of my work is to actually have access to this theorem in practice, because when I say in practice, I don't want to compute the more Penrose pseudo-inverse. So this is a partial list of different problems that are based on the Laplacian. So there's this regularized inverse here, there's the degrees of freedom, and the effective resistance. There are other things. I work also on the spectral estimation, so I want to estimate the eigenvalues of the Laplacian without paying the cubic cost of diagonalization. In this talk, I'm going to concentrate on one problem because this is the easiest to talk about. So this is why I chose this one. Which is the estimation of the degree of freedom of Qi plus L of the linear smoother K. Okay, so big K here. Keep in mind that it's always equal to this thing here inside the trace. To simplify, I'm going to suppose that Q is constant over all nodes. So this big matrix Q, which is diagonal with positive entries, I'm just going to say it's small Qi with Q real. Nice to keep in mind as well is that, so all I'm going to talk about, it works for any matrix Q, degree diagonal matrix Q. It works for other types of Laplacian, so there are some normalization that you can have in mind. For instance, the degree normalized Laplacian, which is here, d minus half L d minus a half. This is one other type of Laplacian that it works indeed in this case as well. And even more generally, it works if L, so you want to compute this thing here. It works even if L is a diagonally dominant matrix. Okay, it doesn't have to be a Laplacian of a graph. You take any diagonally dominant matrix, and what I'm going to talk about will still function. Okay, it so happens that Yit Pilafchi, which is my student, will discuss some other problems than this one here. He will discuss graph Tikhonov regularization this very afternoon here in the ENS, the machine learning signal processing seminar. What I didn't say at the first slide are the people I work with. So this is Yit Pilafchi, my PhD student, and I work with Simon Barthelmé and Pierre-Olivier Amblard in my own lab. I work with Alexandre Godillère as well, who is in Marseille, and with Luca Avena, who is in Leiden University. Luca and Alex are probabilists, and Simon, Pierre-Olivier and I are, I don't know, signal processors or applied mathematicians, I would say. I don't know how we define ourselves. But this is really a collaboration between probabilists that have been working in the last decade on random spanning forests and ourselves, who kind of try to see what can those forests be useful for. So this is the presentation slide, let's say, of the actual work that I'm going to present. So the goal, once again, is to compute this trace, this inverse trace for large graphs, so say n superior to 1,000,000. So you need to compute an inverse, which is out of question here. So the state of the art is a combination of Hutchinson's estimator and iterative methods such as precondition gradient, conjugate gradient methods. I'm going to talk about this briefly at one point in the presentation. And in this work, so the originality is to present Monte Carlo estimators that are very different in spirit from the state of the art. State of the art is very general for this precondition conjugate gradient works for any matrix L which is SDP. In our case, it's less general, so we cannot use our work or our ideas on such a general class of matrices such as SDP matrices, but we can. But they are just very original in a sense. The spirit is very different. This is what I like about this work. So before I go into part 3, I need to give you a few basics on random spanning forests and especially in notations, because we don't have all the same notations and I don't have the same one as Adrien. So let's go. So for what is a forest? So I have a graph at the beginning, an underlying graph. The spanning tree, as I said before, is just a connected spanning set of edges that does not contain any cycle. I'm going to talk about rooted spanning trees, which is just the choice. Given a spanning tree, I choose a node and I say this is a root, and I orient all edges towards this root. A spanning forest is a union, is a disjoint union of spanning trees. And a rooted spanning forest is I choose a root per tree in this forest. And there are many, in the same sense, in the same way there are many spanning trees in the graph, there are even more spanning forests in a graph. Given a spanning forest, I'm going to call, so the forest is called phi in general. I define rho phi, which is a set of roots, the red nodes. Okay, so this one here, and this one here. And I define the root function, but in fact, I'm not going to need the root function, so forget about this second line here. Just rho phi is the set of roots. And I consider this the following distribution of forests. Why this distribution? This is very closely related to the uniform spanning tree distribution. I'm not going to explain exactly why, but this is very closely related to USTs. So the distribution is the following. So phi sub q here is my random variable, and it equals phi with a probability that is proportional to this product of weights of the edges that are in the forest times q to the power the number of roots in the forest. Okay, and very importantly, especially in my talk and in my endeavor here, is that sampling a forest, such a forest, is fast. Okay, you can sample such a forest in a time that is roughly linear in the number of edges. Okay, this is very particular. This is not true for DPPs in general. This is kind of a miracle happening here. In general, sampling a DPP on a ground set of size n, it takes n cubed. You need to diagonalize the whole thing, the kernel. Here in this case, you don't have to do this, and I still don't really understand why. I mean, there's something profound here that I miss. Okay. I'd be happy to talk about this later if any of you have some insights. But in our case, we're very happy because we can access random spanning forests very fast. Okay, and this phi q here is called the random spanning forest in general. So maybe I'm going to give...
Nicolas,
yeah.
So it's for q tends to 0 that you get a spanning tree?
Yes.
So here it means that your complexity is blowing up as q tends to 0.
Yeah, because so in Wilson's algorithm to sample USTs, what he does is he takes a Q, and then he goes to 0 with Q until he has a connected one component. So he stops at some Q. And the algorithm I'm going to present right after this, which is the modified Wilson algorithm for random spanning forest, it blows up as Q goes to 0. Because there's the first part where you just walk around the graph until you root yourself with probability Q. And if Q is null, then you just turn around forever. But in the modified Wilson I'm going to present here, it does blow up when q goes to 0. In Wilson's paper, which is a bit different because he wants to sample USTs and not random spanning forests, he has some turnaround, some workaround to not blow up. So Wilson, okay, I call this Wilson's algorithm. In practice, it's a modified Wilson's algorithm. It's not exactly the one he proposed in his paper. It goes like this. I'm giving it to you. I mean, I find this algorithm beautiful. So you have a graph here, and I'm going to walk through the little steps. So first you add a node, an artificial node, let's say, called the delta, and you connect it with weight q to all nodes. Okay. Then you start from any node, and you propagate a random walk until it reaches delta. Okay, when I say random walk, is when I arrive somewhere. Here, for instance, I have some probability to go to this neighbor and some probability that goes to this neighbor. That is proportional to the weights. Okay, this is a very natural notion of random walk. So say I start here, the bottom here, and I do my random walk. Okay, so I walk around. Of course, eventually I stop, unless q tends to 0, where I don't stop, and the algorithm just turns forever. When I stop, I erase loop. Another name of this algorithm is kind of a loop erased random walk algorithm. So I erase this loop here, okay? And I keep the selected edges and add the last node before delta to the set of roots. So this here will be a root, and those two edges will be in the tree rooted here. Okay, I keep this information. And then I iterate this thing. I start in a new, I do another random walk. I start anywhere that I didn't visit yet, that is not in red or in blue here. I start here, for instance, and I do my random walk until either it reaches delta again, or it reaches what I've sampled already. Okay, in this case, I reach something that I sample, I stop here, and I iterate this process. After erasing the loops, there was no loops here, so no problem. So I iterate, I start here, and I do my random walk. Here in this case I have one loop, and I reach delta, so I erase the loop, and I keep this new node as a future root. Okay, and I iterate this process, and at the end I have a spanning forest, which is random, and which follows the distribution I just gave you just before. Okay, the sampling cost, we actually know the expectation of the number of steps of this process. It's exactly equal to this trace here. And it's bounded by n plus 2 times the number of edges divided by q. Okay. Now, two key properties of random spanning forests. So this matrix K, it plays a central role in the theory of random forests, and among them are other things. The root process, so the row of phi q, if I sample a random forest and I only look at its roots, is a determinable point process with marginal kernel k. Exactly this marginal kernel here. Which implies several things. The entry I of k is the probability that node I is a root. The trace of k is the expected number of roots. Okay, so you're probably seeing where I'm going with this is that this trace of k, I don't know how to compute it very efficiently, at least in large n. Okay, this inverse trace operation. But what I can do is sample a random spanning forest, look at its roots, not even its roots, look at the number of roots. It's even simpler, and I have an unbiased estimate of what I'm looking for, trace of k. But this is part 3 of the talk. Another very interesting property is this one here. The probability that I is rooted in J is controlled exactly, which is also remarkable, and it's equal to Kij. The entry Ij of K is the probability that I is rooted in J. And we actually use this property here for Tikhonov regularization that I'm not going to talk about. Okay, so now I can enter part 3. I started 40. I have like 10 minutes.
15 minutes. Yeah.
15 minutes. Okay. That's fine. So our objective is to compute this trace. So I recall that trace of k is the expected number of roots of the RSF. So I have almost freely, once I have written those equations here, a trivial RSF-based Monte Carlo estimator. this is the algorithm. You draw big N independent random spanning forest, and you compute the average of the number of roots, and you're done. It is unbiased by this property here. And you can actually have access to its per sample variance just because it's a DPP. So you have all those information. Now the state of the art in this case is a combination of Hutchinson's and some algorithms just such as PCG, so preconditioned conjugate gradient. So how does it work? It works like this. You draw also big N independent random vectors, small x here, that verify that this identity covariance here. Now what you do is you compute the average of x transpose kx. Let me forget for now how I do this, okay? Because I recall that k is this thing here inside the trace, and how do I compute this is the whole problem from the start, right? So let's say I have some oracle that gives me x transpose kx. Well, in this case, it's unbiased, okay, because the expectation of x transpose kx, well, of the Monte Carlo estimator is the expectation of x transpose kx, which, because its identity, has a covariance of identity, which is equal to trace of k. So this is the concept of what we call Hutchinson's estimator, or Girard as well. I mean, both people wrote independently this estimator a few decades ago now. And we have access to a per sample variance in the case of Gaussian entries of this x here, which is equal to this. Okay, for now I'm just giving the equations. Now the problem here is that I need to compute x transpose kx, okay? And this I do via several techniques. We could use sparse Cholesky, we could use polynomial approximation, preconditioned conjugate gradient to solve, well, the kx part, okay, where you have to compute this inverse times x. This is the state of the art. Okay. So what can I say about, if I want to compare both approaches? There are several things to say. One of them is that, okay, well, the per sample variance here compared to this one is spectrum dependent. So there's not a lot to say. I mean, it depends here. So the denominator is the same, but the numerator is different. Here it depends on q lambda I. Here it's q square. So, I mean, you don't really, it's hard to say. It's hard to tell exactly which one is better. You can plot those things for different graphs. I mean, it's not that interesting. What is interesting to remember is that both the state-of-the-art and RSF based are linear, are in time linear in the number of edges. And if I look at other differences, one of them, the one I like most personally, is that this RSF estimator is trivial in a sense. The implementation of the algorithm takes 20 lines maybe just to do the loop erasure, the loop erase random walks. But then counting the number of roots is trivial. The footprint, the memory footprint is absolutely minimal. I mean, if you have memory enough to actually store your graph, you have way too much memory already to just do this algorithm and count the number of roots. There's no pre-processing of the graph. And in fact, there's no centralized knowledge of L. This is very interesting. Preconditioned grading, poly approximation, all those techniques that are general in linear algebra, they require the knowledge of L. The globalized knowledge of L. Okay, maybe I'm not very clear here. So what I call globalized knowledge is I have in mind one computer that has the entire graph in mind, in memory. When I say that RSF-based estimator do not need centralized knowledge, what I mean is that if I'm on a sensor network where each sensor has its own information, I can propagate, the operator can connect to any sensor, say start a random walk, loop erase random walk, and this random walk goes neighbor to neighbor. Okay, the whole operations here that I actually do is draw a uniform random variable and go to your neighbor that corresponds. Okay, and in the end, the operator does not need to know the graph. I mean, this is a fundamental difference I find between the two versions here. Notable disadvantages of RSF estimator compared to the state of the art. So it only works for diagonally dominant matrices and Q larger than 0. So if Q is inferred to 0, well, you will have problems of stability in other ways, but you can't do this with RSF estimators, or more general matrices you can't neither. What's also annoying is that even if theoretical complexities are similar in a sense, RSF-based estimator use the computer in a very different way. Okay, so doing L times X, so matrix vector computation, has been over-optimized for the last 50 years. This is probably like the basis of computation in a computer. And here I never do that with a random walk. Okay, so this kind of iterative process is not adapted to modern architecture. But this is it's annoying, but that's how it is. So if I want to compare, so those figures here date back from 2019. I didn't put the new figures because we've been improving this simple estimator. We've been improving it over the last few years, and now we actually do better in most cases than the state of the art, even in seconds. I mean, even if you don't count the number of operations, we actually count the number of seconds that it takes. So five methods to compare. There's RF, or random forest, direct, which uses the backslash operator of Julia. If you're familiar with this is a algebraic multigrid method, which is a classical other method, let's say, to solve this kind of problem. This is conjugate gradient, so this is Hutchinson with conjugate gradient. This is Hutchinson with MAG. This is Hutchinson with a precondition that is based on AMG. Okay, those are state-of-the-art methods. That's all you need to know, really. On 5 different graphs that have 10,000 nodes and 100,000 edges. And for fair comparison, we look at, because all of those are stochastic method, I'm actually giving myself from the start an epsilon, an error I allow myself, and I count the number of seconds the algorithm reaches this relative error. Those are 5 different types of graph. The circle, grid 2D, grid 3D. Barabasi-Albert is a random graph that has a very broad degree distribution. Noisy heart, I don't remember what it is. Okay, and we see that, so this is trace of k, and the x-axis and y-axis is number of seconds. So this is parameterized by q, of course, by small q here. And we see that we are faster than the state of the art, especially when q is large. And when q is small, well, we have this problem where it just runs forever. So when q is small, this is not, well, other methods explode as well for stability issues mainly. But all methods explode, but ours explode faster. So for small q, you need to find other things than random spanning forest, or at least the way we do it. So maybe so okay, so this is, so I recall that my main goal here for the last few years has been this following problem where I have a graph and I want to compute things. Anything, really. It could be the maximal degree to the whole spectrum of the Laplacian to whatever. Well, here I have an instance, which is the trace, the inverse trace of this operator, L. And I give you one algorithm that works based on random spanning forest. And now the following question is, to what extent am I able to actually compute things on the graph? What am I able to retrieve from those random spanning forests? What is the extent of everything? I want everything, right? This is the kind of the big picture behind this. What have I put here? Okay, so before I go to other things I can actually compute or we've been working on, a few remarks. One of them is that there are some classical variance reduction techniques that you can use on this problem I've just showed. On the simple estimator, you can improve it using very classical techniques. More importantly, this algorithm that I called Modify Wilson that samples random spanning forests, it can be modified to actually sample a trajectory of random forests between some scalar q min to a scalar q max. Okay, so instead of giving yourself one value of Q and sampling the forest or the random forest associated to Q, you give yourself an interval, Q min, Q max, and you want to sample a trajectory of random forest throughout the whole interval. What is remarkable is that, so this is the cost here, n plus m over Q is basically the cost of sampling one forest at a given Q. And this cost here, n plus m over Q min plus n log d max over Q min, this is the cost of sampling the whole trajectory between Q min and Q max. This is very powerful because this additional cost here is peanuts compared to this, to m, usually. I mean, n log d max is usually smaller than m, the number of edges. Okay, so with a almost trivial additional cost, you can actually sample a forest on a continuous interval between Q min and Q max, such that you can, for instance, have access to an estimation of the whole function on a given range using exactly what I've showed you. Okay, and this is so a precise comparison with state of the art is currently an object for a future publication, and it's actually quite hard to do a fair comparison with state of the art because you need to kind of reinvent tricks for PCG, for a preconditioned conjugate gradient. The naive way of using it would be, okay, I give myself a grid between Q min and Q max, and I compute the whole thing for each value between Q min and Q max, and I use PCG every time. This is not very efficient, and so we need kind of to ourselves make research on how to improve PCG in this special case in order to have a fair comparison. Okay, so it's kind of tricky to actually do this comparison here, but this is an object for future work. So as a conclusion, so we have state-of-the-art performance for inverse trace estimation. Okay, this is kind of not the major point that I want to transmit here. The computation cost is okay. Is similar to the state-of-the-art with this problem of exploding in small q, which can be can probably be turned around. I mean, to be avoided by using multi-scale approaches, or I don't know exactly how. So what I like about this is that it's very simple. The memory usage is extremely low. And there's no pre-processing, there's no centralized knowledge. All those things make this algorithm very elegant, I find. And so in the project I'm in currently, we've been working on how to do graph Tikhonov localization, so not computing of the trace, but computing k times some vector. We've been working on effective resistance estimation using random spanning forests. We've been working also on partial spectral estimation using random spanning forests. This is current work, either published or being published or very soon. Okay, so this is, the opening is, what is the extent of the information I can retrieve from a few random spanning forests? Another big point, and this is there's many links with what you presented, Adrien, this morning, is are there other similar DPPs over edges and or nodes of graph for similar objectives? So I can define a bunch of DPPs over edges. Which one are Wilsonable in a sense? Which one can be sampled very fast? Because this is kind of the foundation of all this work. I mean, it's Wilson's algorithm. And if some of them are Wilsonable, by Wilsonable I mean linear and over edges, basically, what can I extract as a type of information? So we've been working currently on forests of unicycles, for instance, some generalization, but there are many interactions that I'm sure will be fruitful. So thank you for your attention. And
thank you, Nicolas. Questions?
Yes, I have a question. So given a sample, does the order of the computation matters?
so
Because if you say if you sample one root here, but in the later you need to justify the touch the previous, let's say in the previous the red one. So it
So-
means that the order
Yeah. It seems so, but no. No, and this is the profound result by Wilson, really. It does not depend in the order in which... So the first node you start from, this one is arbitrary. It's not even random, it's arbitrary.
Yeah, actually I'm curious about because I'm a guy of parallel computing. So I'm thinking of if this can be parallel to compute just one sample.
Ah.
So that's why if the orders matter, then this is a sequential computation, and it's hard to parallel.
So no, the order does not matter. Now the question of can we parallelize Wilson's algorithm, I've been thinking about this, and I think no, for several reasons. So in some cases you can. I mean, if you have basic one is a disconnected graph in two components, you can run Wilson parallelized on both sides. Now in some less extreme cases where you have two big communities, there's a high chance that the bridges between those two communities will not be sampled by my random spanning forest. Or there's a high chance that this happens, but just because there's not a lot of edges. And I can do parallel on both communities and then kind of figure out what I do in the middle. But those are approximations, and I'm pretty sure there is no way of parallelizing exactly Wilson's algorithm. Yeah.
Sorry, I ask this because I do some kind of the PCG, that type of stuff.
Yeah.
That can be parallel computing. But yeah, that's what I'm curious.
Yeah. Okay. Yeah. Well,
You said that yes, it's just approximation. Maybe in the stuff, if
there are ways of approximating Wilson's algorithm in a parallel way. Sorry. I've been thinking about this question, and I've been thinking of several different ways of doing this. I've seen a few papers even that try to do this. Okay, there are approximations, so then it's another story. But okay. Yeah. It's a very interesting story, though. I mean, but how it's... I mean, this kind of naive idea where I separate the graph in two just because there are two communities, well, that's already very hard to do. How do I find those communities such that I can run Wilson on both sides? Right. So here, it's kind of... I mean, running Wilson is so fast that any pre-processing is kind of destroying the whole utility of using Wilson, right? If you need to spend n square to actually find those communities in order to parallelize Wilson, then forget it. It's useless. So it's very hard actually to find a fast pre-processing for Wilson, just because Wilson is so efficient already. Yeah.
So your setting applies to weight the graphs?
Yes.
Can you do it with direct weighted graphs?
Yes, you can. And the easy question is I'm not comfortable in this setting just because I never think about it. It's hardly sufficiently complicated with non-directed graphs where everything is symmetric, where the spectrum is real, everything is easy. The whole theory, so here I kind of give this question to Alex and Luca who are not here. The whole theory behind it works for directed graphs, but there are some pits there where you don't want to fall, and I don't master this problem. So yeah, in this instance here. Yeah, even for the inverse trace, I always consider symmetric matrices. So everything is okay, maybe a simple way of doing this, of answering this question is everything here can work for diagonally dominant matrices. There's a standard trick in the literature where you can actually transform a diagonally dominant matrix in two Laplacians associated to two different graphs. So if your matrix is diagonally dominant, it works. Yeah.
Questions? If not, let's thank Nicolas again.
Okay, so first of all, thanks to the organizer for setting this nice workshop, and for giving me the opportunity to present those results. Yeah, so I'm going to talk about mainly edge mode in the 2D and 4D quantum Hall effect. And if time permits, I will spend some time at the end on counting statistics. So this is a work done in collaboration with Benoît Estienne and Blagoye Oblak. And most of the talk will be about the paper in the middle here in Cyprus Physics. And if, as I said, if time permits, I will mention also the other two. Yes, and slides plus chalk means this is mostly chalk, but I thought it would be nice to show some pictures, perhaps to help with the presentation. Okay, so this is a simple plan, 2D, 4D, and then counting statistics. Okay, so there were already a few introductions to quantum Hall effect, in particular by Nicolas. This is an experiment that was carried in the 80s. So I'm talking here about what's called the integer quantum Hall effect. And so you apply some very large magnetic field, and in some units you realize that the resistivity is almost perfectly quantized. So it means that the resistivity transverse rho xy is in units of h over e square, experimentally very, 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 very close to an integer. And this is one of the nice phenomena that occur in condensed matter physics. And there was a huge amount of work to try to explain it, generalize it, and so on. So in this talk, I won't have much to say about experimental results, but this is the background, if you want, that motivates from afar what I'm going to do. And so one way to get this integer quantum Hall effect is to do quantum mechanics. So for me, there will be in this talk, most of the talk there won't be any interaction. So it's all described by a single particle Hamiltonian with momentum p. So you have to add a magnetic field, and the way this is done is through some vector potential, and there is some known machinery on how to do it. But basically, you have this Hamiltonian to diagonalize, and it's sufficiently simple that you can do it. And so here you have this magnetic term here, and I put some trapping potential, which has been done a lot in many of the talks here. And naturally, so it's a sequence of steps. You have to consider large magnetic field. There are Landau levels you project and stuff like this. But at the end of the day, for this particular problem, the single particle wave function you get. So for me, z, I forgot to say, but z is essentially x plus iy. So it's 2D. I'm in the plane, and I use complex numbers to label coordinates. And you get this simple wave functions. And since it's a free fermion problem, basically so this is a workshop on determinantal point processes. So it induces some determinantal point process with a correlation kernel, which is a projection kernel, and is constructed out of those single particle wave functions. And by the way, by some coincidence, it coincides exactly with the Gini-Bro ensemble for random matrix. So the correlation kernel, or the propagator, or the two-point function in physics parlance for this problem coincides exactly with the correlation kernel for the Gini-Bro ensemble. Okay, and here I just show the correlation kernel. I'll just write it down completely explicitly. And one nice thing about it is that if you're is that it's so explicit that you can do a lot of exact computation in some limits. So basically, with this, it has been studied to. I would even say it has been studied to death, and really a lot of results are known both in physics and in math. on this. And for me, so there is a huge literature on this, and I will focus on one tiny but interesting aspect, which is the edge, what I call the edge physics. So first of all, so this is the correlation kernel, and if you do z prime equals z, you get back the density. And what is well known is that basically for large n, all this density is constant in a bulk, which is will be here a disk, and outside it is very, very, very small. So I use units where this density will be. So for me, I will use unit where basically the radius of this disk will be order square root of n. So I want interparticle distance to be order 1, which is why I use this unit. So often people rescale by some factor n to get just a unit disk. But this is what I will do. Yes, and here I just show a picture. Really, this is what I'm talking about. So I plot. So just the next few slides I just plot. I plot the density profile, okay, for this problem. And yellow basically means maximum density, and blue means 0. Okay, so there is a color code, and you see it's almost constant density, and then at the edge, it reasonably quickly goes to 0. So I forgot for how many particles I did, and I call n the number of particles. And for I forgot 100 or something, and you get this. And okay, so this is well studied, and what's also well studied is the asymptotics of this kernel in the large n limit. And so in this picture, what I do, so I if you want, I fix some point which I call z0, okay, which will be here in the middle, and I make a plot just of when z is anywhere in the picture, okay. And so it's the same. So here, and you see that the yellow color means it's relatively big, and blue means it's really 0. And you see it decays very fast. Okay. So, and this is a simple computation which you can do. Convince yourself that this decays fast. And what I want to do is just to move this closer to the edge, okay, of my circle. And if you do this, you get something funny. I hope you see it. So here I just move it horizontally. And here you see that the edge actually it doesn't decay so fast. So there is some kind of you see in the picture that it doesn't decay very fast, and in a way that's what you could call a signature of an edge mode. So basically the precise statement that you can make is that if you so in this unit where my edge would be, so if I put, okay, so here I put square root of n exactly. I could move away a bit from the boundary, but the statement is if I parameterize my edge like this, okay, and I send n to infinity. You get, okay, I take modulus because there are many complex numbers and phases, and I get some constant which you can compute explicitly over sine theta over 2. And I ask that e to the I theta is different from 1. Okay, and this is what you, so in a way, the kernel in the bulk decays extremely fast. Okay, it decays Gaussian, and at the edge, it decays much slower. It's a power law, so 1 over square root of n, and you get this scaling, which is and sine theta over 2, if you want, is some kind of chord length that connects. So here I have a point here and here, and if I had a point here, sine theta over 2 is just this length. Here, I hope you see like this. So it's just like this. Okay, so and that's what I wanted to say. So that's all for the slides for now. Okay, and if you want, so this result is not that surprising, but if you're like me and you come from conformal field theory, this is very natural, because the one way to interpret this is that there is some kind of effective conformal field theory which lives at the edge, okay, and it has a power law decay of correlation. And this is a sort of an old story in physics, and there are many results in this direction. So, for example, you can consider more complicated wave functions, which were so I think this was explained also in some previous talks. So you can do generalization of this, let's say, wave function like this. So here, this is the many-body wave function. So it's the Slater determinant, if you want. So if beta equals 1, this would be the Slater determinant constructed from my single particle wave functions. Okay, and so this, and if beta is say 3, 5, etc., this wave function was first written down by Laughlin to explain something more complicated than what I want to talk about, which is the fractional quantum Hall effect. But basically, this is a wave function, and if you take modulus square, you have some probability density for particles. And it's equivalent to a log gas, and it's a generalization of the Ginibre ensemble. But this type of scaling you expect to hold also at the edge of such more complicated wave functions, for which you can't compute things explicitly because you don't have determinants anymore. So there are many generalizations, and there are many more complicated wave functions. So you can write wave functions similar with where you add extra factors like Pfaffians and stuff like this. So there are many wave functions in fractional quantum Hall. In the fractional quantum Hall business, if you want. Some are better than others, but all of them are supposed to have this power law decay of correlations, and it's related to conformal field theory. Okay, so I won't actually talk about conformal field theory, but it's conformal in the following sense that, so here it's if you think back in terms of these wave functions, here you could see this as some kind of log gas. So you say it's exponential of log of some I less than j zi minus dj. So here you can see as some kind of external potential, which has not necessarily anything to do with the potential I wrote in the Hamiltonian, but this is a potential for the log gas. And you could modify the potential, and if you modify the potential, you might modify the shape of the droplet, okay? But what will happen is that you will get generalization of these results for correlation at the edge, which are obtained by, okay, there is a calculation, but basically they are obtained by doing a conformal map of the exterior of the droplet to the upper half plane. So this was, I think, first mentioned by, I think that was first pointed. There are papers by Jankovici where he claims that. There are, on the physics side, there is There is a famous paper by Wigman and Zabrodin, and there is also a lot of math on this. So I'm not an expert, but I think there are several works by, in particular, Serfati, with statements that come close to this. And for the free case, so for the determinantal case beta equals 1, I think there is a recent paper by Hammer and Kronwall, where they exactly prove this statement. So if you want, what I'm talking about for now is a very simple particular case of this. Okay, but this is just to tell you this is where I come from. So there were lots of nice talks where it was mostly bulk physics, and the edge was sort of a nuisance for the statement you wanted to make. And for me, it's the opposite. I'm more edge kind of guy. And yes, and I'm going to make another seemingly weird statement, which is that from this perspective, all the points at the edge, they are connected, in the sense that if I take 2 points exactly at the edge, so square root of n, I can shift by some order 1 also, and the formula are modified in a known way. But for simplicity, I will just do this. All points at the edge, they are connected in the sense that if you want, I take this limit and I get something strictly positive. Okay, and worst case, it's infinite if I take the two same points, but it's connected in the sense that take this limit and it's strictly positive. If I were to do this in the bulk, I would find 0. Okay, and what motivates this work is a simple try to do a generalization of this to similar model that could happen in a 4D. And so while staying very pedestrian, so the point of this talk is not to make big claims about 4D quantum Hall effects and stuff like this, but I will try to find the simple generalization, the simplest generalization, to 4D of the model I talked about, and I will apply the same logic. I will be motivated by edge physics and edge physics only. And so you can try to do the same in 4D, and okay, so there is an analog construction as before, so you need a vector potential. So a very simple model will have, I don't think this works, okay, anyway. A vector potential like this, and my coordinates are x, y, u, v, and with this I can do two complex numbers. So if you want, an opposition in my 4D space is labeled by z and w. Okay, and if you apply the same logic, so there will be again Landau levels in this simple model I wrote, and you will get single particle wave functions, and they look awfully close to the one I wrote. And this is the main motivation for considering such a simple model, because I mean the potential we put is very, very symmetric. So already it's harmonic, so it's and it's very, very symmetric. But actually the new thing is that you see in H there is a parameter k for xy plus y square, and there is a parameter k prime for u square plus v square. And the novelty, if you want, is that we don't do k equals k prime. So this is a very tiny generalization of this, and you can diagonalize this. So in some limit, you have to project onto large magnetic field again, and stuff like this. You get this wave function, and they have this energy with frequency omega, which are given in some units by the ratio k over b, and omega prime is k prime over b. Okay, so this is the single particle spectrum. And before going on with my study, I just want to say that it's not completely crazy to consider generalization to 4D of the quantum Hall effect. Of course, we live in a 3D world, but so this has been studied at the beginning. I think it was very theoretical. I mean, just people were asking, can you do a quantum Hall effect in 4D? And turns out there are analogs of this in 4D, and so this was put forward in this 3 papers. So there is a paper by Sushen Zhang, I think, the first one, but he considered a model which is a bit more complicated than the one we considered. And then later it was studied in this. There are many other papers, but these two considered this simple model I was talking about. And there are more formulating this in terms of effective field theories and stuff. And here it's more just concrete wave functions. And there are proposals. So I think this was there was a question yesterday about this. And there are ways at least to mimic higher dimensions. So it's called synthetic dimensions, and there are a few tricks where you can try to imitate the effect of dimensions. For example, by having extra internal states and coupling them in a certain way. So I mean, I have to say that for this, it's mostly discrete stuff, and here I consider continuous wave function, so it's still a bit far. So I don't want to make a claim that you can do what I want to do in the lab, but just that 4D is not completely academic in principle. Okay, and what I get with the same strategy as before, I want to do the exact same thing. So yes, so I had my little computations here, and they were really very easy because I didn't tell you how you do it, but it's essentially before it was essentially application of Stirling formula for the factorial and stuff like this. So it's not very complicated. And here I want to do the same with this kernel, which is a bit more complicated, but it's still completely explicit. So I can hope to do some calculation. And now the difference I have is that I have an extra parameter for the ratio of my two trapping frequencies. Okay, so I have something to play with, and the correlation kernel, which would be if you want the 2-point function of the ground state, or the correlation kernel I want to study, is given by this sum. So I need to select. I have two quantum numbers now, m and n, and I need to select numbers for which m plus delta n is less than some big number n. So if you want big N here will play the role of chemical potential. So chemical potential, and I take all the states that are below. Yes, and as before, I want to take n, big N goes to infinity. Okay. The difference with before also is that n is not a particle number now, because the number of particles is determined by the number of ways in which you can do this. So if you want, the particle number is roughly proportional to n squared, like this. Okay, and I want to study, and I want to look at the edge of this. So now it lives in 4D. Okay, and I think that's yes, that's all I have for the slides, for now at least. Okay, and you can ask yourself, so for example, what's the analog of the droplet? So before, the droplet was just this disk, okay, which I didn't rescale, which has a size roughly square root of n. And you can, and with this, it's all again an easy computation, because I mean, with this, I didn't say it, but many of the bulk properties you can get just by saying that the sum runs to infinity. Okay, so here there is a constraint on the sum, and if the sum runs to infinity, you see you reconstruct part of the exponential, and then in the end you get only exponentials. Okay, and what you get is what we call a squashed. So if you just think of the density profile, what you get is a squashed three sphere. Okay, so basically, so I have two complex number ZW to label position in my 4D space, and they, as long as they satisfy this, so it's squashed because of this parameter delta, but otherwise this would be. I forgot it's n here. Okay, so it's completely analogous to this. You replace the one sphere by the three sphere. Okay, good. And the point of this talk is that if you try to ask similar questions to my edge correlation from before, then you get interesting new phenomena. Okay, which okay, so now I want, so I have perfect. I have this this kernel here, and I want to parameterize some points at the edge. So what I can do is that I can parameterize. So here it's the edge is located roughly at square root of n. So there is a bit of parameterization which you have to do. And one way to do it, I think, is like this. So there is this e to the I beta sine theta over 2. Okay, so it's like it's known. It's like if you come from quantum physics, it's like parameterizing the wave function for a qubit. Okay, like this. So this is a point on the with okay, you choose appropriate intervals for theta, alpha, beta, etc. Okay, and this would be one of the points. And since I want to look at correlations along the edge, so this is my first point. If you want, this would be the z, and I need z prime and w prime also. Okay, so I need to choose 2 points on this free sphere, and so it disappeared from my screen. Why? Yes, and so I can do, for example, this. Okay, and here I didn't put alpha and beta because you see that in this kernel it's always z complex conjugate z prime, w complex conjugate w prime. So if I were to put alpha prime and beta prime here, everything would depend on alpha minus alpha prime and beta minus beta prime. Okay, so just for simplicity, I do this. Okay, and you can ask the same question as before. So are this, in this sense, are the points connected in the sense I was talking about just by working with this kernel? And so I can tell you a result, which is the first thing is that the first thing is that this. So if I want to do the same, I compute. So it turns out the relevant scale is also square root of n here, and if I do z prime w prime, so I sent n to infinity. Okay, with z and w, z prime w given by this here. So it's 0 if modulo I forgot pi or something like this. So you get something different already. Is that here all points at the edge were connected? They were talking to each other in the sense of the picture I showed before. And here, if you do that in 4D, you might think, oh, I get some complicated 3-dimensional edge theories, which I don't know, might be, which you might think, maybe it's some complicated field theory, it's nice and everything. And then at the end, so already what you get is that theta must be theta prime. So there are lots of edge modes, if you want, that don't talk to each other. Okay, so you get this. And okay, so if I have this, I can define. So let me do this, and now I define this. Okay. So edge kernel, if you want, Kn. So with this condition satisfied, theta is theta prime, and now I define this like this, and this is what I study in the following. Yes, and it implicitly depends on theta, but this is the dependence on alpha and beta I want, and I can give you the main results if you want, and then I will tell you how you. Okay, so if you want now, everything depends only on two numbers alpha and beta, which are periodic because these are phases. So basically, everything is parameterized by a torus. Okay, and the result is that okay, and maybe I should do this. so that I avoid the problems. And the problem, and you might ask, okay, so which points are connected in that sense, are talking to each other, and for this to be strictly positive, you need an extra condition. So I needed to impose that theta prime is theta, and you actually need another condition, which is, I think, this. So there must be a relation between alpha, my angle alpha and beta, which means, in a sense, I have only one parameter left, okay, for my edge modes. And so it means, really, when I do this 4D quantum Hall effect, the edge is a 3 sphere. But actually, what I would like to interpret at edge modes propagating on my 3 sphere, they are completely one-dimensional at the end of the day. So it's not a 3D theory; it's rather a collection of one-dimensional theory. And you get an analog of I erase this. You get an analog of this, okay? And so this one is a bit. More complicated to state. Okay, and so if I satisfy this condition, so that I'm on, I will show a picture where these are actually trajectories on the torus. Hopefully it will help. If e to the I delta alpha equals e to the I beta, then k alpha beta is going to be some constant over sine. Okay, so I will write this like this, and t, I will explain what t is. So you imagine I have a like this. Okay, so let's say I parameterize alpha beta between minus pi and pi. Okay, so this is minus pi, minus pi, pi. Okay, and I have a trajectory. So the simplest one is delta equals 1, which was known from before, where basically the trajectory is just this one. Okay. So I would travel like this. Alpha has to be e to the alpha has to be e to the I beta. So it means I'm traveling on this one. So if you want this an edge mode that connects like this on this torus, but you can do something a bit more complicated. So let me try to do one picture. So for example, you can do delta equals 2 or 1/2, one of those two, I forgot. So you imagine that you go like this, e to the I, something like this, and then it's on a torus, okay, it's periodic, so it means you come back here. Okay, if you come back here, then you're here. You come back here, you're here, and here. Okay, so I think this is delta equals, I forgot. Yeah. 1 chance out of 2, it's 1/2, but okay. You do it, and here it's the same. So there is a 1D, the points they are connected along this 1D path, if you want. And it's just some torus on some trajectory on the torus, and since it's simple, it comes back to the initial point. So if you imagine you start from here, okay, this is your starting point, then you travel like this, you go like this, you go like this, you go like this, okay. And t, so I have to explain what is t. So t, so there are explicit formula, but you can interpret t as some kind of time it takes to go from one point to another along the trajectory. So imagine I start from this one, and I get to, I don't know, this one, for example. So I imagine I have some guy that travels just at constant speed on this trajectory, okay? And t is just the time it takes to reach from this point, with the convention that if I do the whole trajectory and I come back to the initial state, the time elapsed is pi. Okay. So this and it's analog of this. Okay. So here it's the same actually. This sine theta over 2. You imagine you go at constant speed along in 2D along the circle here, and with the convention that if you go back to the initial points, it's time pi that has elapsed. Yes?
So I have two questions. First, you don't do any renormalization for kn in the alpha. There is no square root here.
Oh, sorry. No. There is. Sorry. Yes, I forgot. Yes. Square root. And yeah. Sorry. Thanks. Yeah.
And then another question. So did you say you restrict yourself to delta an integer? Or,
So I will. This will be what comes next. Yeah. So and yes, and basically, I mean, it's a very very basic ergodic theory. But if you consider trajectories like this on the torus, the trajectory they depend hugely on whether or not delta is irrational or not. Because if it's irrational, you will always come back to the initial point. Otherwise, you don't. Otherwise, you will feel it's ergodic. You will feel the.
So your result is for any delta, or it's for delta rational?
Yes. Thanks. Yes. So and here I assume yes. Oh, thank you. Because I want to talk about irrational later, but yeah, sorry. I assume delta is rational for this. And maybe it's better if I show what I did on the. I show plots. Okay, and this is I do something similar. So I plot this correlator for the largest n I can do. It's just and I do a plot and on this torus. So I take points at the edge which are parameterized like this. Theta prime equals theta, and the only degrees of freedom I have left are alpha and beta. And here is the same. You see these trajectories, okay, which are which if since n is finite, they are a bit blurred, and because it's quantum mechanics. Okay, this is delta equals 1, and then you can play around with lots of values for delta. Delta equals 3/2, 5/3, etc. And so you can go to more and more complicated fractions. So this is yes. So this is what you get. What? How much time do I have left?
Until 25.
Okay. Yes. Thanks. Yes. So basically, you can do it. And this computation, you can do it for delta rational. For delta irrational, we didn't manage to do the computations till the end, but there is a natural conjecture which I will give. Yes, what is this plot? So this plot is so since visualizing things in 2D can be a bit complicated, I simplify even further the problem by just showing a plot of a slice. Okay. So I forgot which slice it is, but and you see here, if I do a slice plot, I get only a few values where it's where the resulting kernel. So I fix some beta, let's say, and I plot as a function of alpha, and there are only a few places where this is supposed to be non-zero. So the plots they are for finite n, but the dots they are the predictions from this formula. And okay, and for this set for 17/12, I forgot you get maybe 12 points or 17. I forgot. It has to be consistent. But basically, you get this, okay. And the more complicated the fraction, the more complicated the patterns. And there is a natural conjecture that if you were to do irrational numbers, you will get a function which is highly non-regular. So it would be some kind of crazy function, like an indicator function for rationals and stuff like this. And in that case, the conjecture would be, so if delta is not a rational number, so the k alpha beta should be some constant, which you can have explicitly this time over time. So you do the same thing. You think you assume you travel at constant speed around the torus. And it's this, and it's not the sinus of the time, but the time it takes to reach, with some convention for units, but it's in the constant, so it doesn't matter. So you have this funny thing that the sign is replaced by t, and of course you don't necessarily, if it's irrational, you don't go back to the initial place. So yes. Okay, and this is the function. So if you do a slice plot of this, you will get an infinite number of values where it's not zero, but it's the function is still 0 on almost surely. Okay, and so I think that's all I wanted to say. No, so maybe just one second for just how you compute this. So just give. So I give the argument in 2D, but in 4D is the same. So I had my in 2D I had my wave function which were like this. Z to the m over square root of, I think, pi factorial m. Okay, exponential minus z square over 2. And basically, I mean, you can make this rigorous without too many difficulties, but basically these are wave functions which are very localized. So we want around, for large m, this holds. If you plot just the modulus square of this wave function, it's localized around essentially square root of m. So you compute the maximum of this, and you see it's localized like this, and which means that for the edge correlations, you can guess which m matter. Okay, and so the whole game, since my kernel is of this form like this, phi m of z star phi m of z prime. You can easily guess that the modes that will contribute, I mean the indices that will contribute to this edge mode will be located very close to n. Okay, and so this you can rewrite if you want. So I can do like this, n minus m. Okay. And now I think I go from 1 to n, so it's the same sum. And if I parameterize, so where do I have this? If I parameterize, let's say z equals square root of n e to the I theta, z prime square root of n e to the I theta prime. Well, I just need to use, I alluded to this, but I just need to use essentially a Stirling formula. Okay, so I will have this, and this will be, if I apply Stirling formula, I think something like this, theta minus theta prime over, so the square root will come from Stirling's formula actually. Okay, so I give the really hand-waving argument, minus k square over 2n plus, okay, so dot 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 means subleading corrections. Okay, and roughly speaking, the sign you get just by, sorry, this is not k, it's m. Okay, so you just, this estimate you get just by Stirling formula, and basically the result you get just by promoting the sum from m equals 1 to n, saying while it goes to infinity, okay, then you get the geometric series, and so you get 1 over 1 minus e to the I theta minus theta prime, which gives the sine theta over 2 at the end of the day. Of course, you're not allowed to do this because the series doesn't converge, but you can work out that the term I wrote allows to regularize the sum. So okay, you have to do it more precisely, but basically at the end of the day, the result will be just the geometric series like this. Okay. And in 4D, well, it's more complicated sum. You have to arrange the sum differently, but you can do it. And in the, I think, 5-10 minutes I have left, I will show an application, a simple application of this to counting statistics. Which it always goes back to yes. Yes. So one thing. So I told you. So now I will go back to 2D for simplicity, but you can make similar statements in 4D. So I told you I had, at least in the units I was working with, all my particles were, so if you want the droplet, all my particles were in this disk with radius square root of n, okay? And there has been a huge literature on counting statistics in similar problems. There are many papers, including by Gregory. And what we did to emphasize the role of these edge contributions, why to consider region A, which is just this. So it's just the angular, it just points in the complex plane such that their argument is between 0 and some angle theta. Okay, so it's this region here. Okay, and you can study counting statistics in this problem. So there are many related problems. Actually, our motivation was not even counting statistics. It was more entanglement entropy, but it's more complicated versions of the same. And you can compute this random variable, which would be the number of particles in A. Okay, so this would be, I think, could write this something like this. Okay, Zj in A. Okay, so you count 1 if if the points are in A and 0 otherwise. Okay, and you can compute, for example, the particle variance or the second cumulant for this. Okay, and so and if you were to do this in the bulk, it's reasonably well understood what you are supposed to we are supposed to get. But here we expect also a contribution to particle fluctuation coming from our edge correlations, right? So because I was insisting on the fact that correlation decay power law at the edge, so it must have some effect on the particle fluctuations in such a geometry. And the nice thing is that it's easy to make conjectures for this, even for the Löffling states I was talking about. So even for generalization of this. Okay, so if I do this, I less than j, zi minus zj. So this is the wave function I wrote before with beta, which can be, so 1 is a determinantal point, but beta can be something else. Zj square. Okay, so this one. Yes, and I should say for beta equals 1, what I will write I can prove. But otherwise I can't prove. And you want to look at this for large n. Okay, so for large particle number. How does this scale? Okay, and so T beta. So that will okay, and so the leading contribution will be square root of n. Okay, and in physics it's called area law. Area law, why? Because if you want particles, they fluctuate, and to the leading order, what matters are the fluctuation near the boundary between A and its complement. And here, since I work in units where the disk has reduced square root of n, if you want the main contribution will be proportional to the boundary between A and its complement, but inside the droplet, because outside there is nothing. Okay, so this is to the leading order what you would expect. I think if you instead of the region I talked about, you take a circular region. Gregory has done the asymptotics to all orders, I think, so it's very nice and simple. You can do it to all orders and have all the correction. So in that case, it's a bit more complicated, and I again lost it on my and T is some constant that depends on beta. And the prediction is something like this: 2 pi square beta log square root of n sine theta over 2. Okay, and this subleading contribution comes from the edge mode I was talking about. You can do a computation and find that this comes from the edge behavior I was talking about. There is an extra term, and I will finish with this, I think. Minus theta over 4 pi square beta plus a constant. So this is my notation for saying there is a constant which depends on beta but not on theta, plus okay, so if you want, this is like a conjecture, okay, which holds for any beta. So for the Löffling state, and you can do it for even more complicated wave function, I claim that this asymptotic expansion holds. Okay, and just and this is, so part of this are a long story, but this if you want is the edge contribution. Okay, so this comes from the edge I was talking about during the whole talk. This is called area law. Yes, and this is and this puzzled us for a long time because we were thinking at the beginning that we would only see this, and it turns out in the constant there is an extra contribution, which is this weird factor here, and we understood recently that this actually comes from the corner which is located here. So the point is in the asymptotic you have to be careful what you assume on the boundary of the region A, and here the boundary of region A is not smooth. There is this corner here, and it impacts the asymptotic expansion. But if you were to consider a smooth, I don't know how to say, but a smoothened version of this, where, for example, you do something like this, where there is no sharp corner, then this term would disappear. And so, and we have some understanding of what you can do. I should say also that this area law, there are theorems, there are general theorems on this in even more general context. So the area law, in that sense, is not really new, but the funny thing was the edge impact. And with this, I think I'm over time, so I will stop.
Questions for Jean-Marie? Yeah, Nicolas?
So, well, I have a few questions, so stop me when I'm over time. So, suppose what I've heard very often is that the edge of fractional control states should be different than the integer control states. There should be some overshooting of the density close to the edge.
Yes.
Like that. Is it something that I'm supposed to see in this formula, or is it completely?
No, I don't think it's. Yeah, so here for me it's very important that the points they are very far apart at the edge. So whenever I do asymptotics, I need to assume that e to the I theta is not. So I mean,
I thought
yes.
the overshooting was just when you go in the direction when you cross the boundary.
So for example, in 2D, my 2 points that I chose often are this. And in the asymptotics I showed you if you rescale, you find this. So it's clear the formula cannot hold if theta is 0. So if you want, there is a change of asymptotics. So you can see it in the. So if you want to do the asymptotics of the kernel, there are basically three regimes. There is bulk regime, which is easy. There is edge, but where on the points they are close to each other. And there is edge where the points are far from each other. And these are 3 separate asymptotic regimes.
So the non-trivial difference is really only when you are on the edge, close to one or 2 points very close.
Yes. Yes, you can do it also by saddle point, and you see there is some change in. Yes.
A more general question. What is it that one measures in the 4D quantum effect?
Oh, this. I think they're yeah. So it's not.
I checked on
Yeah.
Wikipedia. There are experiments. So I would like
Yeah.
to. So I would like to know what they're measuring, if you know.
Well, it's not really clear to me, to be honest. So it's not even clear they really realize the 4D quantum Hall effect. But the point is that they are able. So I think they do at least they do like discrete models. So you imagine like some kind of Chern insulator version of this. And I think, but I don't think they're able to measure. Maybe I'm wrong, but I don't think they measure edge currents or stuff like this.
Yeah, but they must be measuring something.
Yes. Yeah. So I have to confess, I don't really know what exactly they measure, but.
Yes, in your formula for the variance, so there is also there must be some contribution also that comes from the edge. I mean, from the second regime that you mentioned. No? So. Is it only contained in the constant that you want, but it should also depend on that as well.
Yeah, so I think it enters only the constant.
But it does not depend on.
Does not depend on.
It does not depend on the